the electricity needed to supply the consumer. Okay. Now when you get wind blowing, you don't know when it's going to blow. Okay, you get the sunlight. That's also a random source. So the renewables has one significant factor is that the source is random or stochastic. We know the user side has been stochastic, right? You can have some statistics, but still you don't have a way to know when it's going to consume more because the weather will change random. Okay, so now we have an issue about the supply side and the consumer side are both random. They're both stochastic. And I mentioned earlier that we have to balance them minute by minute. So how would you do it? If you generate more, if there is strong wind coming up now, you want to make sure the wind energy is captured, right? You don't want to throw them away. But there's not many people are using it now because it's just a strong wind. So how would you do it? How would you save it? You try to store it, okay? You try to store it, so that brings up the issue of energy storage. And that would be really, really important with this new alternative energy framework, okay? And of course, there's the other source, the other case, which is the supply is not bigger than the demand, okay? Or the demand is bigger than the supply. That could be time like that. And in that case, if you can somehow regulate the consumption side to make sure that they can respond to what you set up, either through price or through contract or through something, so you can control their demand. That is also a strategy to balance the supply and demand equation. Okay, so that is a strategy we can use as well to balance the whole energy equation, and also that's what we do for demand response. Okay, so that's a long story. So it's basically we have to, with electricity, have to balance the supply and demand equation there, and minute by minute. Okay, so you may have heard about this electric cars or this hybrid plug-in electric cars. That's one source of one way to store energy, right? However, I'm suspicious because you don't know when the guy needs to drive the car and the battery is out. So he might charge it during the non-time or when everybody is using electricity. So that is it's also a random source. Okay, if you use that as a storage is not going to be controllable entirely. Okay, so that brings up another issue that I'm going to talk about, which is the topic today. So now let's look at the whole picture. We said, during the peak hours, 30% of the electricity are consumed due to air conditioning, and those are the largest consuming factors. If we're trying to regulate the demand, or we're trying to somehow store the energy, we should perhaps look at how do we store energy that's going to be used for air conditioning, right? If we can somehow shift the peak load that's caused by air conditioning to a different time window, then we're solving the problem. And we don't have to store it in the form of electricity. We can store it in the form of thermal energy, because air conditioning is turning electricity into thermal energy, right? Into a thermal form. So that's the problem we're talking about today, is that if we can somehow use the structure of buildings that has huge thermal capacity to somehow regulate the power consumption or the energy consumption into a different time than the 3 o'clock in the afternoon, then we're helping solving the problem. Okay, we're helping solve the problem. So that is the issue here. We're trying to use the thermal mass of buildings to perhaps shift the peak load of electricity to early during the day when everybody else is not using that much electricity for air conditioning, and then you're keeping your building cool during the afternoon. And then you use less energy or power during the afternoon. Okay. All right. There are some people who have worked on this problem. Actually, it's very hard these days. I know you guys are grad students. You're trying to pick up a research topic, right? It's very hard to pick up one topic that nobody has worked on. Okay. There's always someone who has worked on it. Something that people have worked on. So this one has been worked on, like from Purdue, Lee and Brown, Professor Brown's group has looked at open loop control, optimal control issues, try to set up what would be the best strategy to set up your thermostat during the day so that you minimize your energy consumption. And there's the building thermal energy storage study from, this is Colorado, roughly a few years ago. It's not that old literature there. And from ETH, Professor Morris' group is also looking into the problem with how to make use of this weather forecast data for building control. All these solutions, they are trying to do the same thing, basically trying to somehow to adjust the temperature set points in the afternoon so that you don't consume as much energy during the afternoon, but you're still comfortable with the temperature, okay, with the room temperature. So the idea, one of the ideas is actually using pre-cooling here. That is to use more, cool the temperature down a little bit more during the morning, so that later on you can have it gradually rising up, but still within the comfortable zones of the residents or the occupants of the buildings. Okay, so this range here is what you have to consider, which is the temperature range that you still feel comfortable, but you have some room to move around, and people would not notice it. Okay, so those are the sort of strategies by designing some open loop control ideas and then set it up for maybe the whole day and the whole week operations. Now I want to bring another thing that we can play with for those of you who are working in control. Why feedback is needed? Why prediction is needed in this scheme? Okay, we say there are uncertainties in many factors. Those are the major disturbances for this problem. Weather is a major disturbance for HVAC consumption, air conditioning consumption. Okay, load factors, whether this room is packed with people or it's empty, that's different. Okay, and then there's a consumption pattern change. It could be, for a convention center, maybe the whole building is occupied or there's not many people inside the buildings. So there are uncertainties in those factors, and some of them are predictable. So you could use a model to predict them. Some of them are measurable. Maybe you can use wireless sensors to measure the load. How many people are walking into the room and walking out. You can do head counts there. So there are strategies we could use to handle those uncertainties. But when you get those information, you have to somehow adjust your control strategy. That's where we need feedback control. Okay. So that's really our objective is that we want to be able to reduce the energy cost and demand cost there, and reduce basically the thermal capacity of the buildings and design strategies so that we will satisfy all the comfort requirement, but also we save energy. So the load factors could be simulated, and also the lighting. Lighting is a big factor. It's consumption of energy. It's also a source of heat, right? All those lights, they're not very efficient in lighting, but they generate a lot of heat. So that's actually a big factor. And there are other electrical equipment that also consume energy. And then for the external factors that affects the HVAC control, is that the ambient temperature is one, and radiation is another. For the same ambient temperature, whether the building has a lot of windows or not, that makes a lot of difference. Okay, for an office building, if it's all glass exterior, that's the worst. That would consume a lot of air conditioning energy there. Okay, so these are the factors we will need to consider as load changes, and for control, we have to deal with these load changes and try to make sure our temperature is always, or most of the time, within the comfortable zone. The control strategy we're proposing here is to use the model predictive control, as we could build a model from data or experiment, or maybe from first principles, and then use this model-based control to regulate over a 24 period of time. Most buildings, commercial buildings, are operated in a 24-hour window because during the night nobody will be there, so you could relax the constraints and then start up a new day, just like the airplane operation, the airline operation. They are not in day and night. You have a sort of batch operation that way. Okay, so it's just a quick introduction of model predictive control. It has a few things. One, it uses predictive model to predict what's the impact of what you change, and also impact of these disturbances. And then it has an optimization algorithm to minimize optimal control target objective. The third is that it's subject to constraints. So it enforces upper-lower limits for the input variables and also maybe state variables. So it does have the optimal control framework, but has the constraints explicitly enforced. That's the idea of model predictive control. It's been very successfully applied to a lot of the petrochemical and refinery industries. I had a paper in 2003 that had a survey of all the industrial implementations of model predictive control. That was a big surprise to a lot of the control community there. So just going to bring up the project structure. Before we work on the real building for the student, we start with a realistic simulator. This is Energy Plus. You can download it from DOE or some, this is actually sponsored by DOE over 20 years. Energy Plus is a very now proven software for simulating realistic buildings. You supply all the parameters, dimensions of a building, then you can generate the output that you would need from a building. Okay, you can get actual temperature, power consumption, and demand, and other things. The input side are the things you can set maybe for the temperature of a particular room or particular zone of a room, and so on. And then in this case, we're setting it using a control strategy, a control that is model predictive control strategy to set up the temperature set point, so that we're trying to produce an optimal set point profile over the day given the real-time feedback, and then adjust it so that we minimize the energy consumption cost. Okay. So here's another software we have to use. It's called middleware, DCV-TB. This is also developed by a different group. We're using it to make the data communication between the simulator, the Energy Plus, and the MATLAB in real time. So it's like it's going to work just like a real building control system. Without that, you can only do it batch-wise, which would be inconvenient for control simulations. So the building we start from, this is a large building. We say it's a single floor building, but a large dimension. We get the zones divided into 5 zones. Usually, this is the case where when it's closer to the windows, you have a different temperature distribution dynamics in the interior of the room or the building. So we have these 5 zones, and each zone, we assume it has its own thermostat measurement and also the control, the vent that control the temperature and so on. Then we do have to set up the model. What is the impact of increasing 1 degree of that zone at the thermostat? How much electricity is going to consume, or more? How much more electricity is going to consume, and what's the dynamics of reaching that new consumption, new temperature set point, and so on. So we have the HVAC, the air conditioner thermostat in place, but we're just manipulating the set points of those temperatures. Okay, so that's our MPC strategy. It's a supervisory level. Okay. before we go into the actual control